Good day, we're Team 14. I'm Lakshay.
I'm Josh.
I'm Elliot.
I'm Jason.
And we're all electrical engineers. For the PCB design, unfortunately, we're unable to use this design for the final project. However, some interesting innovations were included. As directed, I added 3 separate polygon pores to separate the 3 voltage requirements of the 3 sections of the PCB. These sections were the motor power, servo control, and the driver circuits. These 3 sections were all connected to the star ground. The connectors were all placed on the outside of the PCB to make testing and connecting our components much easier. Bluetooth capability was also included on the PCB. For the soldering process, we started from the middle and then proceeded to the edges of the board to make the process much easier. Also, another important portion to consider when soldering was placing the correct silk screen labels to each component so we can make sure that all the components are correct. All parts and component placements and wires were checked by my group mates before ordering the PCB from JLC PCB.
For the vehicle design, we used the Texas Instruments Robotic System Learning Kit, or the TI-RSLK for short. We mounted the motors and wheels to the ROMI chassis and connected them to the motor driver and power distribution board equipped onto the ROMI chassis. Since we moved from an initial 4-wheel 2 DC motor and servo design, there is a front ball bearing included on the ROMI chassis to provide extra stability. Using the pins on the motor driver and power distribution board that we pre-assigned in the code, we connected the OpenMV line scan camera and the HC-SR04 ultrasound sensor to the distribution board. We then chose to mount the OpenMV line scan camera and ultrasound sensor to the ROMI chassis by making a rustic Bohemian design using sturdy wind sticks so as to decrease weight we would have put on if we were to opt to use a 3D printed mount.
For the writing and the testing of the code for the ROMI chassis, the first challenge in writing out the code during the winter quarter was that we were preparing to build the car on a separate platform, which would have been the 4-wheel 2 DC motor on the rear wheels with a servo to steer the front axle. In contrast, the ROMI chassis that we ended up using was only using 2 wheels with a ball bearing wheel at the front. This meant that the code needed to be changed in order to accommodate for steering the car using relative speed differences between these 2 wheels. Because of this, the code had to be optimized such that the outer wheel either sped up or the inner wheel slowed down in order to turn a corner. This made the code somewhat simpler. However, it required a lot more testing to find the optimal pulse width for the motors when turning. The final values we settled on were that the outer motor would run at 100% and the inner motor would run with a 70% duty cycle. Both motors ran at 100% when the track was straight to ensure the fastest possible time around all 3 tracks. Using 1 region of interest instead of 2, we needed to make sure that the loop repeated fast enough for the car to instantaneously detect the lines on the track and turn into them. This made the car's movement a lot smoother and faster, rather than jittery and sudden, which it was when we first started testing the car.
For the obstacles we faced during the trials of the camera detection, initially, the camera couldn't detect the white tape we placed on the tasting racetrack. Because the initial setting of the camera was not able to detect the white blob, we had to tweak the settings and the range for it to detect and differentiate between light and dark spots, for it to be able to detect the racetrack we built. We also had to tweak the rotation speed of the motors, since the racetrack we made curved at a greater angle than the one that is placed on campus. Because we used 1 ROI instead of 2, the loop does not process fast enough for the camera to be able to detect the white lines and then to be able to determine which motor should slow down and or speed up. We had to slow down the rotation speed when the car is driving straight for it to be able to process the line as well as determine what to do with the 2 other motors. After all the tweaks we made to overcome the obstacles we faced, we eventually made the car to be able to operate within the standards of the specifications given from the class.
Now let's see this race car go around the track.
Ladies and gentlemen, here we go. And we're off, screaming down the first straight into the first corner. A nice swooping right, smooth through there. Front wheel just about staying on the ground. That's a sharp left, but it makes it a wonderful turning radius, a good advantage of the 2-wheel design. Swerving through here, just a few curves, another quick sharp left, makes it absolutely no problem. Here it comes down into a long curving hairpin, takes the left wonderfully, swoops through into the right. This camera is doing a fantastic job at detecting these lines, even on a bumpy outdoor surface. Running over a few cracks here, small wheels have no problem dealing with those. Screaming down into the last straight, and up to the finish line. Perfect performance. Oh, and a bit of showboating here, that's just disrespectful. Let's have a little bit of sportsmanlike conduct. Oh gosh, that was unexpected to say the least.
And on that bombshell, thanks for watching.